I'm Bob Lucas. I'm a Research Associate Professor of Computer Science at the University of Southern California, and I'm the Director of Computational Systems and Technologies at the Information Sciences Institute. The CS&T group does a very broad range of research in computing systems. It includes making chips and programming field programmable gate arrays. We do software like compilers and clouds. We work on smart grids, do wireless networking. We have a satellite in Earth orbit right now, and we are the first people in human history to take delivery of an adiabatic quantum optimization device. USC and Lockheed Martin have a partnership to study the D-Wave adiabatic quantum annealer. So this is the first quantum computing device commercially delivered anywhere in the world. The machine is really a specialized optimization device, and so we've studied it first to understand whether or not it's really a quantum device, which we have ascertained it is. And now the question is it faster than normal computers for any interesting human problems? And that's what we're working on now. I used to be very skeptical about quantum computing. Now I'm cautiously optimistic. I think we're at the dawn of a new era. And if D-Wave can make such a machine, there's no reason others can't as well. And so I expect to see more and more of this. So I'm a high-performance computing person. I'm particularly interested in linear solvers. Basically, for 30 years, I've been studying how to solve bigger problems faster. There's no bound to the imagination of scientists and engineers in terms of the scale of the problems they'd like to be able to solve. And so this ranges from everything from making cars safer to making engines more efficient, modeling the climate, developing new medical technologies, cures for cancer. All these things are things that bigger and bigger computers would enable. For the Department of Energy, I lead SUPER, the Institute for Sustained Performance, Energy, and Resilience. So it's a group of 4 national laboratories and 7 other universities, and we're trying to basically alleviate the tedious human burden imposed when porting codes from one large-scale computer to another. As technology changes, we change the way we build large-scale computers. So when we transitioned from bipolar to CMOS devices, we fragmented the memory. Now we're adding accelerators like graphics processing units, and that changes the programming model. So all this requires human labor. Software and labor are more expensive than the computers that they're running on. And so anything that alleviates the cost of porting codes will save a lot of money and a lot of tedium. Everyone's familiar with the term Moore's Law, the exponential growth and performance that we've enjoyed for half a century in computing. What Moore's Law really was reducing the size of transistors. They get smaller and smaller. As we reach the end of Moore's Law, we won't be able to make arbitrarily more circuits anymore, and we're going to have to use them more efficiently if we want to continue to increase performance. That'll be as disruptive a change as we've seen in 20 years, and I think ISI has the broad range of expertise that will enable us to lead through that transition.